Hey everyone, in this AP Chem series video, I'll show you how to compare nuclear charge and effective nuclear charge. To do this, you need to remember that there's a difference between core and valence electrons. The valence electrons are the outermost ones, and you'll find them in the highest energy level s and p orbitals only. Take these tellurium atoms, for example, which have the configuration shown here. The valence electrons would be those in the 5th energy level s and p orbitals, meaning tellurium has 6 valence electrons. That also means that the entire other set of 46 inner electrons would count as tellurium's core electrons. In this video, we'll learn what nuclear charge is and what core and valence electrons have to do with it. We'll start with the easier of these two terms, and that is simply the nuclear charge. It's often symbolized with a capital Z, and the definition is really simple. It sounds a whole lot like the term itself. Nuclear charge is nothing more than the charge of the nucleus. Since a nucleus is only made of 2 particles, protons and neutrons, which have no charge, that means the whole charge of the nucleus, the whole nuclear charge, is only caused by the protons. You simply count them up. Let's apply this by comparing the nuclear charges of these 2 atoms, argon and chlorine. You'd go to the periodic table and see that argon has an atomic number of 18. That means it has 18 protons. That means its nuclear charge is plus 18. If you did the same thing with chlorine, you'd see it has 17 protons, therefore a nuclear charge of plus 17, and you can make the statement that argon has a greater nuclear charge than chlorine. The effective nuclear charge is a little more complicated. It still uses a symbol capital Z, but with a subscript EFF for effective. So a good way to think about effective nuclear charge is the charge of the nucleus, but combining that with the charges of the inner core electrons as well. Take this chlorine atom, for example. Its effective nuclear charge is like saying, let's ignore these outermost valence electrons and just think about the charge that results from this plus 17 nucleus and these core electrons combined together. That combined charge will be different than the charge of the plus 17 nucleus all by itself, because those inner electrons will cancel out or shield some of that positive 17 charge of the nucleus. This is often referred to as the shielding effect. To show you how it works, let's draw an imaginary red boundary around the nucleus and those core electrons. We can approximate the effective nuclear charge by starting with the charge of the nucleus itself, the plus 17 caused by the protons. Next, we're going to count how many core electrons there are. 2 in the first energy level, 8 in the second, mean there's 10 total core electrons here that are blocking, canceling out, or shielding some of that plus 17 charge from the protons. Since those 10 electrons are canceling out some of that positive 17 from the nucleus, we subtract out 10 from that 17, leaving us with a plus 7. That is the effective nuclear charge of that nucleus and these core electrons combined. Now, a lot of sources will call this an approximate value, and that is true, but it's also a pretty good way to compare the effective nuclear charges between atoms. Make sure you've taken some time to pause and write down these key ideas. So let's close the video with an example where we compare the effective nuclear charges of 3 atoms, boron, oxygen, and sulfur. The first step is going to be to write the electron configuration of each one. Here's boron, oxygen, and sulfur. This is going to very clearly let me find the inner shielding core electrons. I also need to use a periodic table to look up the nuclear charges of each. Here's boron with 5 protons, so plus 5, oxygen plus 8, sulfur plus 16. And so we don't forget, let's label each of those nuclear charges beneath the configuration. Here's boron's plus 5, oxygen's plus 8, and sulfur's plus 16. So now I know how positive each nucleus is. Next, we need to figure out how much shielding takes place from the core electrons in each atom. I'm going to go ahead and label those inner shielding electrons on each configuration. Here's boron's, oxygen's, and here's sulfur's. So boron's nucleus has a plus 5 charge, but there's 2 core electrons to shield that plus 5 charge, resulting in an effective nuclear charge of plus 3. For oxygen and its 2 shielding electrons, subtracting those out tells me that its effective nuclear charge is plus 6. And sulfur is a much larger atom and has a lot more shielding electrons, 10 of them in fact. Subtracting out those 10 shielding electrons means that sulfur also has an effective nuclear charge of +6. So what kind of summaries can we make here? Well, we know that boron has a lower effective nuclear charge than oxygen and sulfur, and that oxygen and sulfur have approximately equal effective nuclear charges. That wraps it up for this video. Thanks a lot for watching, and here's a brief summary.